So, does anyone have a question? All right, let me just fill in something that I was telling you about last time. How I think of the in and out vacuum states. And the way I think of them is this. You have, it's essentially the same as in the book, apart from possibly a plus or a minus sign, but I'm putting in an I epsilon. And the point of the I epsilon is that it means, remember that we've arranged that we've arranged that H0 on 0 is E0 on 0, and we've also said that omega on what omega on? What am I saying? I've lost. I need a. Can you throw one of those erasers up here toward the front?
You got it.
In fact, if you throw it underhand, I can't.
You got it.
Thank you. I was going to try to catch it, but
then you
I think what you did
does
much better. And
sure can
anyway, we're also imagining that H on 0 is E0 omega. And so the idea is that, you see, because I put in this I epsilon, the E0 terms essentially cancel, or at most they're a phase, and then what you've got is e to the minus t epsilon h acting on 0. And now if we insert a complete set of eigenstates of the full Hamiltonian, this is e to the minus t epsilon h, sum on n, en 0, and this projects out the lowest state. In other words, this is e to the minus t epsilon en, en 0. This is some number which cancels when you take the ratio. Remember, we take a ratio. And this projects out the, so as t goes to infinity, this goes to e to the minus t epsilon E0, and what we call the ground state is omega, and then this is omega 0. So this is the way I think of it. Okay. And it leads to the same final formula as in Schwartz. You might be puzzled by something, namely, why did I say that omega as t goes to minus infinity is e to the minus ith on the state? Normally you'd think it's e to the plus ith. Well, it turns out that in all the quantum mechanics books there's a sort of fairy tale, which, in other words, what we do is we say psi prime e to the minus ith phi. This is the inner product if you have some stated time. This is the inner product of phi with psi prime. I could have left it as just psi after a time t. Okay. What this really is it's the inner product of e to the ith on psi with the state phi. So when you turn this from a ket into a bra, it flips the sign of I. So that's what's really going on in quantum mechanics. And consequently, the state omega at minus infinity, I think of it as e to the minus I th. All right, so much for all that. Any questions? So we were talking about we were about to talk about normal ordering in the last let me get this thing straight here. In the today's Monday, so it would have been last Wednesday. Sorry. Well, what is normal ordering? Well, normal ordering means if you have a bunch of operators, you take the A daggers there, and then you have the A's here. So you put all the creation operators to the left of all the annihilation operators. The reason why this is a nice thing to do is that then you don't, I mean, if you don't do this, then you've got some creation operators in front of some annihilation operators, and then you've got a non-trivial particle, you've got the possibility of particle creation and then particle annihilation that just depends upon the ordering of the operators rather than upon something physical that's going on. And so that's the reason why people like normal ordering. Let me just mention one subtlety about normal ordering that's often overlooked, and it is that normal ordering obviously depends upon the definitions of the annihilation creation operators. And the annihilation creation operators come about from expanding, in the case of a scalar field, you expand this in terms of, b cubed p 2 pi cubed, 1 over square root of 2 omega k. Well, that's 2 square root of p squared plus m squared. And then you say a of p e to the I. In Schwarz's notation, it's this. Okay. Notice, so then you're defining a of p and a dagger of p in terms of phi and pi, the conjugate momentum, which normally is the time derivative of phi in a scale field derivative, and the mass m. The mass m is typically hidden when people think about these things. And so normal ordering depends upon the mass. And the mass that you use to define the annihilation creation operators. All right. Anyway, the natural thing to do, of course, is to define normal ordering in terms of the physical mass of the particle that the field is supposed to represent, and then that's certainly a reasonable choice. Now, what I wanted to show you is Wick's theorem, and I'm going to prove it to you for the case of two fields, and then I'll just wave my hands and say you can do mathematical induction, which is what Schwarz does in one of the appendices. So let's think about the case T1 greater than T2, and now we have time-ordered product. By the way, the deal is that the time-ordered product is a normal-ordered product plus a bunch of contractions. Contractions are basically Feynman propagators, or products of Feynman propagators. So let's see how this works. It's 5x1, 5x2. So that's the time-ordered product. We're going to look at them at this for T1 greater than T2. And here, well, it's of course 5 plus of x1, 5, well, there's a plus sign here. I could write it ultra small, but I might as well do this. Okay, so for T1 later than T2, this is it. And remember, phi plus means you have creation operators, phi minus means only annihilation operators. So the phi minus part is that, and the phi plus part is this. And in non-Schwarzian literature, the convention is reversed, almost uniform. What are you going to do? Now, this thing is to some extent normally ordered. Namely, it's, if we normal order this thing, that just means we put the phi plus on the left. And now we can put phi plus x2. That one is still normally ordered because it's just creation operators. And then we have plus phi minus x2. Okay, so the normal ordering doesn't do anything to these terms. It just leaves them in their time-ordered form. But we've got a remaining term here, and the remaining term is plus phi minus of x1 phi plus of x2. Now this one is not a normal order. Okay. Now what we can do though is we can say, well, how would we normal order this? How would we get normal ordering of the two fields here? Well, we would have to basically subtract this term and add, or to put it differently, if we put the normal ordering term here, what we would do is we would have this structure here, phi plus x1, and this is nothing more than phi of x2, and then to normal order this thing, we would then have plus phi of x2. And then we would, well, no, we've already got everything there. So, yeah, that's right, phi of x2. Phi. I am screwing this up because I didn't write it this way in my notes. All right, let me just follow my notes. The next line here would be that this is the same thing as the normally ordered product of phi x1, phi x2. So normally ordered plus a commutator. And the commutator would be phi minus x1 with phi plus x2. Okay, so what does this do? This thing gives us this term, and then it subtracts out the term that is normally ordered in here that we didn't have on this line. Okay, and this one should be a square bracket for commutator. Okay, so that's the case for T1 greater than T2. For T2 greater than T1, the rule is that the time-ordered product of phi of x1, phi of x2, well, it's got to be the same thing, but with T1 and T2 interchanged, and the normally ordered product doesn't care about the time ordering. But now what we have is the time-ordered product, the commutator of phi minus of x2 with phi plus of x1. Okay, so this is for T2 later than T1. And now what you can realize is that this commutator, of course, is just a number. Because when you take the commutator of this with that, you get the operators go away. You just get a delta function and some 2 pi's. And so what we can do is we can rewrite these formulas by putting in the vacuum of the free theory, we're thinking free fields, free theory here. So everything is the free theory and the free fields. So we can just put in that like that. And, okay, so now what do we have? Now what we have is that the time-ordered product is the normally ordered product plus the mean value in the vacuum of this commutator. And another way of writing it, of writing this thing is, or putting both terms together, is that we get t of phi of x1, phi of x2. So the time-ordered product is a normally ordered product. And then for the case t1 minus t2, it's phi minus, the commutator of phi minus with phi plus, and you can think of it in the vacuum or not, but in the vacuum, only one term contributes, namely the case when phi minus is on the left and phi plus is on the right. So this one is I must say, I think I just sort of, when I was preparing these notes, I just sort of blew through this without thinking enormously. Okay, well, what I have here, let me just repeat what I've got in my notes, because this is what we had so far. And then we also had theta of T2 minus T1. This is actually much simpler than I'm making it. It's just that when I reviewed this, okay, so this is what we actually derived, those expressions. And now we can, since these are commutators, they're C numbers, we can do we can take a mean value in the vacuum, and what happens is we can show that this thing is the same as the time-ordered product of fields in the vacuum, or in the ground state. So in other words, this reduces to that. And so that's Wick's theorem for the simplest case, and then you generalize it by mathematical inductions. This is actually, as I said, very simple. It's just that I've gotten myself just a little bit confused here. Up to here, it's perfectly clear. The question then is, I think I see. Yeah, I think the point is this, that if you take the mean value in the vacuum of the conjugate of phi minus, let us say x, or it doesn't really matter which time it is here because we've got a time ordering thing here. If we do this, then this thing is 0, phi minus x1, phi plus x2, and then minus 0, phi plus x2, phi minus x1. Okay. And that's right. If you can add, I think this is it. Yeah. You add in phi plus of x1. And you get away with that. I don't know. I think I'm going to have to think through this and do it for you at the beginning of next hour. So I've gotten.
Don't you just want to take the expectation?
What?
Don't you just want to take the expectation value of the vacuum at both sides, since the normally ordered goes away? And
That's for sure.
And your commutators are C numbers, so it's just you just get the commutators on the right side.
Brilliant. Very good. You get 2 answers.
Oh, I popped them in.
Yeah, as I said, when I was writing these notes, I just regarded this as trivial and didn't even think about it. And then when I but yeah, so in other words, what he was saying is that we've got on the left, we've got a time ordered product, and on the right, and in the vacuum, the normally ordered product goes away. All right, let me go to the next chapter, chapter 8, and first define what's called an isometry group of a metric space. So a metric space is a space where you have some sort of an inner product that defines some kind of a distance. In Euclidean space, you know, we have our normal distance that FedEx and UPS try to help us cope with. And in Minkowski space, we say that we take either the time component, the difference of the time component squared minus the square of the difference of the space components, or we take minus that, namely the square of the spatial distance minus the square of the temporal distance. Okay, so those are examples of metrics. And so an isometry group is something such that if you have a transformation T, then T of x minus y, T of x minus y is the same thing as x minus y, x minus y. So that's how so this is the metric of the space, and T, if T does this, then it's an isometry, and clearly isometries form a group because if T does that, then you can do it again with a T prime here, and you'll still get back to that. And so isometries naturally form a group, and the isometry group of so the isometry group of ordinary four-dimensional space with the Lorentz metric eta. So in other words, x minus y is x mu minus y mu, x mu minus y mu. So that's the distance, that's the metric summed from 0 to 3. So the isometry group of that is the Poincare group. And the Poincare group is translations and also Lorentz transformations. And Lorentz transformations are rotations and then boosts. So that's the isometry group. And now this is non-compact, and a fundamental result of group theory is if you have a non-compact group, then you can have unitary representations, but they're infinite dimensional. And the basis vectors of a representation
Sorry.
of this group, you're waving to somebody else.
Concrete.
The basis vectors for this are states of given momentum and spin or helicity. And what happens in a translation? Well, translation with a 4-vector A, this will be e to the I A dot P times P and S. And so you see, this is unitary because it's just a phase factor. But the thing is infinite dimensional because you've got infinitely many values of the momentum. And however many values you have of the spin. Wigner back in, I don't know, I think 39, and then Weinberg tightened a few of the nuts on Wigner's proof. And in 95 when he wrote volume 1. And the point is then that these states that form representations of, well, let me say what the Lorentz group, the Lorentz transformation is, then this on P sigma is, I'm gonna just write it in a simple way. It first of all would change the momentum into the Lorentz transform momentum, and then it would be some sigma prime, and we'd be having to sum over sigma sigma prime, and this is a D associated with lambda, and it's typically lambda inverse actually. So it's something like that. I might be off by a transposition or something, but this is what Wigner showed. This is for the case of positive mass. On the other hand, if the mass is 0, then the representations are such that, oh, and I should say, the sum here goes, of course, from sigma prime equal to minus j up to plus j. So these are just the quantum mechanical, these are just the z components of the spin, if you want. On the other hand, if you're massless, then the thing just goes to lambda p plus or minus, apart from a phase, so I'll just write e to the I theta, and I can say what theta is. This is for m equals 0. And so for 0 mass, we have a much simpler situation where you have positive or negative helicity. So this comes from group theory and Wigner and Weinberg some time ago. So let's look at the case of the simplest case, which is j equals 0. And then for this, what we've got is the Lagrangian might be a half d mu phi n d mu phi n minus a half. This should actually be mn squared phi n squared. So there's a bunch of scalar fields labeled by n, and the ng density, or T00, would be partial L partial phi dot n minus L. Well, I'm going to skip. I'm going to just write it as L rather than script L. And this turns out to be quite simple. Namely, it's just the sum over n of a half phi n dot squared plus a half grad phi n squared plus a half mn squared phi m squared. So that's what the energy density is. So this is a spin zero case, and it turns out that it's, as you can see, it's manifestly positive, and there are no puzzles. Now, when we go to spin one, first of all, we've got two choices. We've got either positive mass or zero mass. And the simplest thing is to start out with, is that mine?
Yes.
Yes. Oh my goodness. David Hyde, could you please call my wife instead? Because I'm in the middle of class.
Okay.
Her phone number is the same as mine, but it ends in 50.
Okay. All right.
Thanks, David.
Okay.
Bye. He's a plumber. You always have to answer when a plumber calls. There's 3 categories of people in this country that you have to answer to: plumbers, dentists, and doctors. Anybody else? Say you're busy. So let's see. Now we're talking about J equals 1. And Schwartz says, well, suppose we had a Lagrangian like this. D nu A mu, D nu A mu, plus a half m squared A mu A mu. Well, the equations of motion would turn out to be box plus m squared, A mu is 0. And on the other hand, you see that A mu here is a 0 squared minus a vector squared. And so the energy density would be minus a half a 0 dot squared plus grad a 0 squared plus a half plus m squared a 0 squared. And then it would be plus a half sum on I from 1 to 3 a I dot squared plus grad a I squared plus m squared ai squared. Okay. So this second term is manifestly positive, but this guy is manifestly negative. And so the energy density wouldn't be, the energy density could be positive. And in fact, this thing is basically 4 scalar fields. Because under Lorentz transformation, we could just say that A mu just turns into A mu at a different space-time point. We don't need to say that we have that they behave as, that they transform as a vector field. So they could be 4 scalar fields, or it could be this thing could transform as a 4 vector, but either way, you wind up with an energy density that can be negative. And so the rule, by the way, in physics is you pick an action or a Lagrangian, and then you see what happens. And the action has to the action in general has all the symmetries of the theory. And in fact, that's the advantage of the action. It also gives you the classical equations of motion. And so then you then see what happens when you pick a particular action. You then find out what the symmetries are if they're not obvious at the beginning. And you find out what the energy is and so forth. All right, so Schwartz says, well, let's try to fix this so that we actually have a massive scale, a massive vector field. And so what we're going to do is we're going to rewrite this way: a over 2 d nu a mu d nu a mu. Wait a minute, that should be in plus e over 2 d nu a mu d nu a mu, and then plus a half m squared a mu a mu. Now, you can see right away that there's been a change going from here to here, because these terms, if this term is going to be invariant, then since this is a covariant vector, this has to be a contravariant vector. So it actually does mean that we're dealing with a 4-vector field. Also, you can see that there's a potential difficulty here, because for the space components we have a negative term, which is good for the potential energy in an action. But for the mu equals 0 term, we've got a problem, namely the action density is positive, and we want that to be negative. All right, well, let's see what happens. If we work out the equations of motion here, let me just write down what the answer is. It's A box A mu plus B d mu d nu A nu plus m squared A mu equals 0. So that's the equation of motion, and that becomes, we can extract some meaning from that if we just take the divergence of this equation. And if we do that, what we get is A plus B box plus m squared d mu a mu equals 0. Now, we're going to set B equal to minus A, and so then what we get is this. Whoops. So by choosing B equal to minus A, the box term goes away, and we just get that that this term has to vanish. And that means we removed 1 degree of freedom. And the idea basically is that we could have a theory of this form or that form with general A and B. And if we had it for general A and B, there would be scalar fields and vector fields there. And we're removing the scalar field here with that condition. All right, so what we have left then is we could originally have this with j equals 0 and j equals 1, and it's these guys that are going away because of that constraint. But now, choosing B equal to minus A, going back to this equation and scaling A and B to plus or minus 1, we get that L is half d nu a mu minus a half d mu a mu plus a half m squared a mu. And we can rewrite this in a much nicer form, which reminds you of electrodynamics. We write it this way, except for the mass term, of course. And here, F mu nu is d mu a nu minus d mu a mu. Now this action density is called the Proctor Lagrangian. And the equations of motion then are box plus m squared on a mu equals 0 and d mu a mu equals 0. The energy momentum tensor, well, Schwartz writes it down for T mu nu, but what we're going to look at really is T0, 0. And this turns out to be, let me skip a couple of lines, a half e squared plus b squared after some manipulation. It's that plus a half m squared a0 squared plus a vector squared. So that's nice and positive. But there are three other terms. And the three other terms are a0, d0 of d mu a mu, minus a0 box plus m squared, and may have been integrated by parts here, and then di a0 x0 I. Okay. Well, remember when we're dealing with the energy, we assume that the equations of motion are obeyed. So one of the equations of motion is that, so this is 0 by the equations of motion. Another one is box plus m squared a mu equals 0, so in particular this term goes, and this term is the surface term. And so that means then that the total energy, which is the integral of T00 d cubed x, is equal to something that is positive plus a surface term. And so that means if you have fields that are limited in space, the energy actually is positive because you can evaluate the surface terms where the fields are 0. Of course, if the fields are not limited in space, then you've got a different story. You have to pay attention to the surface term. The same thing happens in general relativity. You get an energy density that's conserved, but of course what's conserved is the integral of that energy density over all of space. There's a surface term, so you've got to pay attention to that as well. And when you're talking about general relativity, the surfaces at infinity often are important, so you have to keep that in mind. Okay. Any questions here? Okay, so the next, let me get a drink of tea and then I'll come back. The next thing to do is to expand this field in terms of creation or annihilation operators, or just to expand it. You can think of it as a classical field and expand that. Schwartz, for some reason, goes to the classical point, but I think I don't really see why he does that. So what we could do is call this what he calls the A minus field. This then is a sum over I integral e cubed p 2 pi cubed, then some annihilation operator of p epsilon I mu of p e to the minus I px. So he has a plus here because he's, I don't know why he did that, but anyway. So P0, of course, is what we call omega P, and that's the square root of P vector squared plus M squared. And one of the things we want from this field is we want d mu, a mu to be 0. And if you take a d mu, you're bringing down a p mu. So what you want then is p mu epsilon mu I of p to be 0. And you basically have, the standard way of doing that is to take epsilon 1 mu. Let me do it for this, for momentum in the z direction, okay, so that it's a little bit simpler. This is 0, 1, 0, 0. Epsilon 2 mu is 0, 0, 1, 0. And then epsilon 3 mu, also called epsilon L mu, the longitudinal one, is, well, one way of doing it is P00E, and the deal is that since momentum is in the z direction, P dot this, either one of these is obviously 0 because the energy component hits the 0 and the momentum hits this 0, so we just get 0. These are the transverse polarizations. This is a longitudinal polarization. And these things are arranged such that epsilon mu is -1. Sometimes one uses complex polarizations. In that case, you say epsilon mu star, epsilon mu is -1. Something interesting, though, there's a bit of trouble here at very high energies, and what you can see is that at high energies, the two components of the polarization vector become very large. They become of order E over m. And so if you have a scattering amplitude where that picks out this component or that component, then you can have a d sigma that's something like, let us say, g squared epsilon 3 epsilon 3, I'll take it epsilon 3 squared, just to pick this one out. And so that's g squared, e squared over m squared. And if this actually happens, namely if we're talking about the weak interactions, and we imagine that we're representing the W, then G here is 0.1, M is 100 GeV, so this is 100 GeV, and then we've got E, and then the whole thing is squared. So if E is of the order of 1 TeV, you can see that you're going to have cross-sections that potentially, as the energy goes up, will violate unitarity. In other words, the probability would be greater than 1. This is something that the colloquium speaker discussed on Friday. I hope you were all at the colloquium. Let me just say that the department spends a lot of money on its colloquia. They're an important part of your education. You should go to every fucking colloquium. Now, if a particular colloquium is really terrible, you have every right to leave in the middle, or after 15 minutes. If it's 15 minutes of garbage, just walk out and slam the door. But you should go for the first 15 minutes. As the speaker on Friday pointed out, what this tells you is that when E is of the order of 1 TeV, you expect new physics, and of course the physics that was found at 1 TeV, well, not 1, but at 7 or 8 TeV was the Higgs. Okay. And of course, calling that new physics is a little bit silly because Peter Higgs predicted this 40 years ago. So, I heard, by the way, from a friend of mine who left a university in England. He was a condensed matter theorist. He went into biophysics and in particular to molecular genetics. And moved permanently to Shanghai, actually. He told me that, I think Higgs told him, or told somebody who told him, that he thought that the English system, which is under, English university system, is under so much stress that if he hadn't made this prediction, he would have been eased out of the department that he was in. And my friend, Waxman, quit his job in England just for that reason, that he was afraid that the same thing would happen to him. Because he couldn't be sure that he could predict another case. All right, the next case though is massless. Spin 1. And so, any questions? So, massless spin 1. We just set him, yes.
Actually, just a question. We got to our discussion about the Higgs boson by looking at these spin-1 particles. And
Wait,
then
say it again?
we got to the Higgs boson, the new physics there, by talking about spin-1 particles. But Higgs itself is a spin-0 particle.
Yes.
So what gives?
Ah, great question. Do you want a candy?
No, thank you.
All right, so let me. The Higgs, you see, the point is that if we started out with a massive spin-1 field and this Proctor-Lagrangian, we'd have trouble at a TeV if we tried to do re-interactions. Okay? All right. What Peter Higgs and others showed some 30, 40 years ago was that you could start with a massless field, which is what I'm about to get to, like the electromagnetic field, where you could start with four massless fields, like 4 electromagnetic fields, and have them transform according to an SU2 and a U1. And then, if you had a doublet, if you had 4 scalar fields, which were formed into 2 doublets, so you had 2 complex fields, and they would then transform under SU2 because SU2 is 2 by 2 complex determined in 1, so they would transform under SU2. And then they would transform into U1 by just getting another phase. Okay? And when I say transform, what I mean is that the action has to be invariant if you make these SU2, U1 transformations differently at different points in space-time. And the only way you get to do that is if you have a gauge theory. And the idea in a gauge theory is that, you see, you would have something like this if we just look at a complex gauge field. Well, no, let's look at the whole bloody thing. Let's make that a 2 by, so phi is phi1, phi2, and each one is complex. Then we want this to be the same as d mu phi dagger, d mu phi, even if phi prime is some group element on phi, where this is a 2-component vector and this is a 2 by 2 matrix. And obviously this isn't going to work if these are ordinary derivatives. But what of course people realized back in the 30s or so, or the 20s in fact, when they were first understanding quantum mechanics and applying it to electrons, that if you change this to a covariant derivative, so that was d mu plus, let me just write it as a mu, and then you would have here and we take this whole thing and dagger it. Then you can have something that is invariant, and what you need is you need this thing, d mu plus a mu prime, or d mu plus a mu phi. This whole thing prime has got to, we want that to be just g d mu plus a mu phi. That will make, so I'm doing non-abelian gauge theory for you, and then we can specialize to the abelian case. But this, you see, is the idea. If this is true, then under the gauge transformation, this thing will turn into just g times that. This guy will turn into g dagger. It will turn into the dagger and then g dagger, and then g dagger g will be 1 if g is unitary. So this is very simple because phi prime is g phi. So all we've got here is to figure out what a prime is, because this is d mu plus a prime mu acting on g phi, that's what the prime means, and we want that to be g mu d plus a. A mu here is going to be a matrix. And so one term is, I mean, if we write this out, let's do the d mu part. You get a term that's g d mu phi, but then you get a term d mu g times phi, and then you get this term, a prime mu g phi, and then over here, this is g d mu phi plus g a mu phi. Sorry that it's so low. Can you sort of make that out? Maybe I should write it, I'll write it again here. You get g d mu phi plus d mu g phi plus a mu prime g phi equals, on the other side, g d mu phi plus g a mu phi. Okay, well this term cancels that term. And then if the phi is always on the right, we can just basically, I mean, we'll satisfy this as long as we have d mu g plus a prime mu g equals g a mu. And that's pretty simple to work out then. It's a mu prime g is g a mu minus d mu g. And now we can get rid of this by multiplying from the right by g inverse. And we get a prime mu is equal to g a mu g inverse minus d mu g g inverse. So as long as A is a matrix that transforms this way, and now you see, if you just had an abelian theory, this would be just a number and g inverse would cancel, as you said. And you just have A prime is A, and then a gradient of a scalar, and that's an ordinary gauge transformation. Now here's the cool thing about the Higgs mechanism. This is the really nice part. Because you see, so far all we've done is said, well, we can construct a gauge theory of a complex doublet of scalar fields. What we can do now, and what Higgs and Guralnick and some others did, I was just thinking, you know, there's this rule that's kind of silly that you can only award a Nobel Prize to at most 3 people. I'm just wondering, and there were about 6 who had a hand in the Higgs mechanism. It's fortunate that none of them killed any of the others arranged to get the prize. All right. Anyway, so what Higgs said was, well, let's have the Lagrangian of the phi fields look like this. Because it's complex, you don't need a half. So you have d mu phi, well, you have big D, sorry. You have d mu phi dagger, d mu phi, and then you have plus a half m squared phi dagger phi, and then minus, I don't know, lambda over 4 factorial if we use, if we use Schwarz's convention. Oh. So now it's quartic. And so what happens here, of course, is that you, as you saw in the homework problem, if you let phi assume a mean value, if phi dagger phi in the vacuum assumes a mean value that's positive, you minimize the energy, because the energy term is lambda over 4 factorial phi dagger phi squared minus a half m squared phi dagger phi. And as you know, when phi dagger phi is very small, this term is more important. When phi dagger phi is big, this term is more important. And so you minimize the energy by having some, what is it, Goldilocks value of phi dagger phi. And the value, in fact, is known that it's of the order of 246 GeV. All right, but now notice what's happened here. You see, you've got this, when I wrote d mu is d mu plus a mu. That's this d mu, again. But you see that. And so now, suppose we just ignore everything except the mean value in the vacuum and just look at this term here. Then what we've got here is, this will be d mu plus a mu phi, and this will be, d mu plus a mu phi dagger. And now the d mu term doesn't matter because we're thinking about the mean value in the vacuum, which is constant. And so this term is just a mu phi, and this term is phi dagger a mu. So there's a term and there's a minus sign. So the Lagrangian has a term in it like this. This is a mass term for a vector field. So this takes, in other words, if the rest of the theory, the rest of the field, apart from this, you have the Lagrangian be this, plus or minus, I don't know, a quarter f mu nu a, where a goes from 1 to 4 for the 4 different massless gauge fields. Then what happens is when this phi assumes its mean value in the vacuum, these terms give us a term like this, where this is just a number. In fact, it's typically thought to be a something like this: 0v a mu v star 0, say, but whoops, that's not very good. 0 v star. Okay, and so this is minus V squared A mu, A mu. And so this is a mass term for the gauge fields. And the way I've done it here is I've ignored the matrices. And so we don't have any, the right structure here. But what's actually going on is that this A mu is A mu A TA, where the TA, there are 4 TAs. One is for the U1 and the other 3 are for the SU2. So there are 3 sigma matrices and then another matrix. And when you, so this is a matrix structure. And so this here you see is a matrix structure. And then you just see what happens when you take this value there. And it turns out that it's a little more complicated than this, namely that you've got one E for the Pauli matrices, say, plus an E prime, the 4th gauge field, times some, well, let's just call it E prime. And the E and the E prime are such that you wind up with a massless field, the photon, a massive neutral field, the gauge boson, the Z0, which has a mass of around 92 GeV, and then a W plus and a W minus, which have a mass of around 82 or 81 GeV. And so the thing that's nice, really, about the Higgs mechanism is that this requirement of gauge invariance, together with the idea that the field configuration at lowest energy isn't the one with the field exactly 0, that leads to masses for the W and the Z. And the masses are related to physical things, the couplings of the gauge bosons and the basic fundamental parameters here of the Higgs action. It's lambda and mu that determine V, of course. V being this thing, which is 246 GeV. And that's the nice part of the Higgs mechanism. The rest of the Higgs mechanism is really awful. And it is the way the masses get to the fermions, okay? The masses to the fermions are psi bar I, psi j, let us say, Cij times, well, it's actually a little better than that. It's, let us say, if the fields are doublets, the fermion fields are doublets, and they are. There's the up and down quark, the neutrino and the electron, the mu neutrino and the muon, and so forth. So they look like this. So what you do is you just, you take your finger and you stick it deeply into your nose and you pull out these numbers called Cij. And the masses then, the mass matrix is Mij is equal to Cij times V, where V is this mean value in the vacuum of the Higgs field. The neutral, one of the neutral components of the Higgs field. And so these are just totally arbitrary. And there's no geometry or anything, so it's just kind of silly. I was going to say something else, but I forgot. All right, any other questions? All right, let me see where I was then. All right, massless spin 1. Maybe we can go over here. All right, so what you do is you just take the Proctor-Lagrangian and you set m equal to 0, and you get L is equal to, let us see, minus a quarter F mu nu. And So now, this is an example of a gauge theory, and in particular, this F mu nu is, of course, d mu a nu minus d nu a mu. And so under gauge transformation, which is a simple gauge transformation, namely a prime mu is just a mu plus d mu alpha, say. So in other words, the idea here, if we go over here to this case, let us suppose that G is equal to e to the I alpha, where alpha is a scalar field depending on space-time. Then, of course, a mu won't change, but over here you'll have minus d mu G. Well, this is I d mu alpha, and then you'll have e to the I alpha, G inverse, e to the minus I alpha. So altogether this is minus I d mu alpha. Now you'll say, where did the I come from? Well, I resisted the standard fetish of sticking in an I. But normally one sticks in the I. All right, so in other words, over here, a mu is multiplied. So my a mu is an I here and another I there. Okay, and that cancels the I. So if a mu changes this way, then this thing is equal to d mu a nu minus d nu a mu, and then the extra terms are d mu d nu alpha minus d nu d mu alpha, and so they cancel. And so you get that f prime mu nu is f mu nu. So that's ordinary gauge invariance. Fields that differ by a gauge transformation are physically equivalent. The equations of motion here turn out to be box a mu minus d mu d nu a nu is 0. And if we look at the mu equals 0 equation, what do we have? We have a mu double dot minus Laplacian a mu, so that's this term. And now if we keep track of these, we get d0 squared a0 minus d0 of del dot a equals 0. Well, the second derivative term cancels, and what we have is simply Laplacian of a0 plus d0 of del dot a equals 0. This is a constraint, and it's a constraint known as Gauss's law. It's a constraint because there aren't any second time derivatives. So it's just basically a relation between velocity and position, and that's a constraint. For example, if you had a ball at the end of a string and you were whirling it around, then the velocity would be perpendicular to the string at each point. So this is called a constraint. One of the things that's annoyed me for decades is that when we teach mechanics, we never tell students about constraints. And then all of a sudden we tell them, well, the real world is nothing but constraints. So, I don't know, the educational system needs work. Now, anyway, this is Gauss's law, and of course you can solve this sort of thing. You can solve for a0, and it's just 1 over 4 pi an integral of del dot a dot, and I'll put a plus and minus here because I didn't work that out. In other words, it's clearly this, because when Laplacian hits 1 over x minus y, it gives a delta function. Okay? This is a Green's function of Laplacian. And so what this tells you is that in general in electrodynamics, if you're in any gauge, whatever, you can say that a0 is a dependent variable, because you can always write it in terms of this. And in fact, more generally, if we were doing this in a theory with charged fields, then this equation would have, it would change. It would be this plus the charge density of the charged matter field. And so whatever you've got, you can basically write A0 in terms of other things, the charge density and whatever that is. Now, the most physical gauge for electrodynamics, in one sense or another, at least the easiest one to understand, has three names. The Coulomb gauge, the radiation gauge, and I guess what, the transverse gauge? What did I say?
Lorentz?
No. No, not the Lorentz gauge. No. Anyway, so the Coulomb gauge, as we said, del dot A equals 0. We make a gauge transformation so that del dot A is 0. So this is transverse in the sense that if you expanded A in terms of momentum eigenstates and epsilon vectors, so A mu is an integral epsilon mu of P e to the I px AP dqp, and I've said h bar c and 2 pi equal to 1. Then you get that epsilon vector dot p vector equals 0. So the polarization vectors are perpendicular to the momentum. But there's more. Two of them are like that. But notice if we set A0 to 0 and we're in a theory without any charge fields, then A0 also is 0. So we have this, the transversality knocks out one polarization. A0 being 0 knocks out another polarization, so we only have two left. And these are the two transverse polarizations of electrodynamics, and typically we write these if the momentum is in the z direction, then they look like this. And then you can take complex linear combinations of these, and those are circular polarization. All right, I think that's enough for now. In any case, we're out of time. Questions? All right, so might as well turn it on.